So up to this point in AP Physics 1, Units 1 and 2, we've been talking about kinematics, this descriptive study of motion. How exactly does something move, what velocity, what acceleration, etc. We've not talked at all about why things move the way they do. And that's where we're really going to start working from here, which is really the more basis of physics as a whole science. So this is going to be one of the most important units of the year, Unit 3, Forces and Newton's Laws. And specifically today, we're really just going to focus on getting some bare bones basics down. So this is really just an introduction to the unit as a whole. So that from this point, we can really step it up and start talking about slightly more complicated things. Before we even get to forces, we really need to have a nice firm definition about what forces act on, which is matter, the stuff that everything is made out of. Now in chemistry, I'm sure you learned that matter had this it's a very textbook definition that it has mass and takes up space. In other words, it has volume. And that's not inaccurate, and we will occasionally think of matter in this way. And additionally, we know that all matter is composed of what we call fundamental particles. Now, when we say fundamental, what we really mean is can't get smaller. Now, you probably learned this in chemistry, as protons, neutrons, and electrons, and that's not 100% accurate, because technically protons and neutrons are actually made of something called quarks. Electrons are not. Electrons, it's as small as you can go. But quarks, and we'll talk about those a little bit more later when we get to, for instance, the electric force. And that worked for chemistry, and it still works for physics, but physics, we want to add a little bit of an extra layer here. And we want to say that we can define matter in two specific ways whenever we're dealing with it like in a problem or something like that. And the first way is we can treat matter as an object. And by that we mean we treat it like a single piece of stuff. And we say it has no internal structure. So realistically, we know if I have like a ball here, this ball is composed of many, many different atoms. Those atoms are all bonded with each other, or at least attracting each other in various ways. But if I'm going to throw the ball across the room and analyze its motion, I don't need to know how every specific atom interacts with all the others to be able to analyze it macroscopically as a whole, as just what we would call just a ball, just a thing of ball. And so we don't really need to worry about any of the inner workings. They're there, but it's not necessary for us to think about those interactions when we're analyzing the motion as a whole. So we can treat matter as objects, where we just treat them as pieces of stuff. The other flip side of the coin is we can treat them like systems. So systems is just a collection of objects that interact through forces. So let's going back to this whole ball analogy. If I had this piece here where it is a collection of atoms, I could treat that like a system of atoms if I was looking at how exactly those behave as a whole. But I could similarly treat it as an object, or I could look at multiple objects and how they behave with respect to each other. Now, the properties of a system are determined by the properties of the objects in the system. We're going to get to what those could be in a second, as well as the arrangement of the objects in the system. If I move the objects around in one way, it might get different behavior than if they're arranged in a different way. And one last important piece we want to add here is that you define what is in the system. Much like in kinematics, where we defined our origin, our 0 point, and our coordinate system, we can also define what is in the system and out of the system. And doing it in different ways might make our problem answered in different ways. So what are the properties of objects that we really need to get down for physics? I mean, there's some basic things that if you look at anything, you're going to notice some things about, but what are some nice measurable quantities that are going to probably be pretty important and we're going to see pretty consistently? The first one is something known as inertial mass, which we abbreviate with an M and a little I. And the inertial mass is what causes an object to resist what we call changes in motion. In other words, to resist acceleration. For instance, over here, if I have a little rock and a big rock, and you over and kicked both of them with the same amount of kick, we would see that the big rock would resist that kick better. It would resist that change in motion. It might move just a little bit, whereas a small rock can't resist it much at all, goes much further, because a small rock has a small inertial mass. And the units for mass, now in chemistry, you probably use grams, but we're dealing with bigger, larger objects, so instead we're going to deal with kilograms pretty much exclusively. Now there actually is a second type of mass we need to be familiar with, known as gravitational mass, which we abbreviate M with a little g. And this causes objects to exert gravitational forces on each other. Now, if I drop my stylus here, it would accelerate downward toward the Earth because of gravity, and that's largely because of the Earth's gravitational mass. But every object has gravitational mass. I have gravitational mass, you have gravitational mass, my stylus has gravitational mass, everything around you has gravitational mass, and it's actually exerting gravitational forces on everything else. But we don't notice those gravitational forces because the gravitational forces we'll learn are fairly weak. You need to have a lot of gravitational mass to notice it. So, for instance, we need to have something with the gravitational mass of, for instance, a planet, where it's like times 10 to the 24th kilograms. So that'd be 24 zeros. So really, really large gravitational masses, or something like the moon. You need really big objects to see this effect. And once again, the unit will also be in kilograms. Now, another one we're going to have is electric charge, which we abbreviate with either a lowercase q or a capital Q. You see both. And this causes objects to exert electric forces on each other. Now, you probably are most familiar with this from chemistry, like protons and electrons. You could have protons and electrons all exerting electric forces on each other. Now, they're not all the same types of forces. For instance, protons being positively charges would repel. Electrons being negative charges would repel. And proton to an electron would actually attract, but these electric forces still exist. Whereas you could have something like a neutron, which has no electric charge, and therefore will not experience an electric force. So not everything has an electric charge, but quite a few things do. And the units of the electric charge, we abbreviate with a capital C, which stands for coulombs, which you spell C-O-U-L-O-M-B-S, like Coulomb's law. Most of you should be familiar with that. Last one I want to go ahead and mention, we don't deal with, those are the three we deal with the most. Occasionally we'll deal with volume, which we abbreviate with a capital V, not a lowercase v. Remember, lowercase v is velocity, capital V is volume, and that's just the space that an object occupies. So if I have, this stylus has a certain amount of volume, it occupies a certain amount of space, nothing else can exist in that space. So the units for that, we usually use meters cubed. In chemistry, you probably use centimeters cubed. And then we also have density. Now, you probably have previously abbreviated density with a D. In physics, we abbreviate it with what is known as rho, R-H-O. It's a Greek letter right here, and it kind of looks like a sad P. And this is how compact the matter, the stuff is in a particular amount of space. So if you have something that's really dense, there's a lot of atoms packed into a particular amount of space. Not so dense, very, very few atoms packed into that amount of space. Now, the units will be kilograms per meter cubed. And we have this equation that you should already know, which is that the density equals the mass of an object divided by its volume. Now, technically, this only works for objects of uniform density, but that's typically what we're going to be working with. Well, now that we've detailed what forces act on, let's talk about forces themselves. Forces are how pieces of matter interact with each other. But let's try to get a more formal definition. A force, which we abbreviate with a capital F, is a push or pull between two objects. That two is very, very important. For instance, this piece of matter here, this ball or whatever it is, can hit this green ball and cause that ball to have a change in motion or an acceleration. So we can have a force between those two balls. Or the green ball can hit the blue ball, same thing. But this is acceptable. But the blue ball can't act a force on itself. It must have a second object there to have a force. It can't apply a force to itself. So you always need at least two objects for a force, and they cause these changes in motion or accelerations. Now, forces are vectors, as we can see here, like this force would be down and to the right. If it went back, it would be up and to the left. So they have both magnitude and direction. So both a size and a direction, up, down, left, right, whatever. And so when we get to adding forces together, we actually have to combine them like vectors. We can't just add the numbers, the directions matter. Now, when we're talking about the magnitude, what is the unit of force? We actually have what is known as the Newton, or newtons, which we abbreviate with a capital N. So you could have a force of 2 newtons, 3 newtons, 10 newtons, etc. We've defined a force, but now let's talk about types of forces. And we're going to go through all the ones we're going to be most likely to see at some point in this class. Then we'll talk about some we won't see in this class too. Now, forces can be really broken down into two main categories. The first category are what is known as contact forces, and these require physical contact between the two objects. The objects must touch each other for the force to exist. So let's talk about a few of those. The first one is known as the normal force, which we abbreviate with an F with a capital N subscript. And this is really the force between two objects pushing each other. So when we think of a push, we're really thinking of the normal force. Now, something to keep in mind, though, is like, so for instance, here I have a hammer, and this hammer is, we'll say, hitting a table. Now, the direction of this table, that's a weird thing to say, like, how does a table have direction? But instead, think about it as the surface of the table is horizontal. Okay, it's not vertical. It is a horizontal table, but the hammer is applying a force vertically. It's applying a force down. So if I look at this, between the force being applied and the surface, it is 90 degrees. So the normal force is always perpendicular to the surface of an object. So if I go over to my wall here and I push on the wall, I'm pushing into it, but the wall is vertical, so those are 90 degrees with respect to each other. Now, this makes sense if you know a little bit of terminology, because the word normal, we're just used to thinking of it as ordinary, but normal is actually a really old school math term. When I say old school, I mean a couple hundred years old school, meaning perpendicular or at right angles. So sometimes you'll even see this written as F with a little perpendicular sign. The normal force is the perpendicular force. So what's the next one? Well, I want you to go ahead and take your hands and put them together. So normal force would be pushing into each other. You're pushing one way or the other, but the surface of your hands, that's a 90-degree angle there. But instead, what happens if we move them parallel to each other? So if I take the surfaces of my hands, I move them parallel, you can hear it, but additionally I start to feel heat. And why is that? Because of the friction on my hands. So the next one is actually the friction force, which we abbreviate with F with a little f subscript. And this is a force that opposes a sliding motion between objects. So if I have my two hands, it's opposing the slide. That's why I'm getting that heat generated. It's opposing that slide. So if I pull this block to the right here, for instance, like a string or something, it is the force opposing that slide, so it goes in the opposite direction. But it is always parallel to the surface of the object. So whereas normal force was perpendicular, the friction force is going to be parallel. Remember, that is the parallel symbol. So it's always going to be parallel to a surface. The next one is what is known as the tension force, which we abbreviate F with a subscript of capital T. Now this is the pull force, but it has to be transmitted through a string, a rope, a cable, etc. So for instance, looking at this block here, if this is like your hand, right here, pulling this, and you pull this block this direction, well, you're not really applying a force to the block directly. You're applying it through this string, rope, cable, etc., but you're still the source of the force. So a tension force is always transmitted through something, always transmitted through that, and it is always going to be a pull force. Like if you try to push something with a rope, it doesn't really work. Additionally, it's always in the direction. So for instance, if I pull it this way, that's the direction the string is going, that's the direction of this tension force. It's always in the direction of the string, rope, cable, wire, chain, etc. Alright, now these last few are a little bit more ragtag. First we have the spring force, which is F subscript S, which might seem a little random. When we talk about spring, I mean literally kind of like a slinky or something like that. And you might be thinking, okay, all these other ones seem pretty common. When am I going to run into springs? Great question. And the next video is going to talk about that, so just kind of hold off on that for now. We have what are known as fluid forces. Now, I'll go ahead and tell you, we talk about normal, friction, tension, and spring in AP Physics 1. We really don't talk about fluid forces in AP Physics 1. It's much more of an AP Physics 2 concept. But this is any force from a fluid, meaning a liquid or a gas, so which includes 1, drag, which is the same thing as air resistance. So if you're moving through something, you get air pushing against you. You have the buoyant force, which is the force that causes objects to float. So if you toss something in a pool of water, it floats. It's being supported by the buoyant force. And we also have lift, which is kind of like the buoyant force, but it's more talking about lifting an object in the air. So if you have something with wings, it's getting lifted up by the air with a lift force. Whereas if you have a balloon doesn't have wings, it's being lifted up with a buoyant force. So anything with wings going to have some of that lift force. Plane, bird, anything like that. Once again, though, we're not going to really talk about those in AP Physics 1. And then the last one we have is kind of a catch-all called the applied force. Now, that's not really a formal name. Really what this is saying, you'll see this subscript is just question marks, is let's say I go over to a chair and I push it. And you say, Mr. Varveer applied a force to the chair. And you might be thinking, well, that's obviously a normal force. Well, it depends on what angle I push it at, right? If I push it downward, then maybe there's some friction force. Maybe I pull it, and maybe you could say there's some tension force in my arm. It can get a little complicated, and you start getting lost in the weeds. And so when something like that happens, we might just say, oh, that's just the force from his hand. Or that is the force from his foot if I kick something. It's something where it could be a combination of all of the above. We just simplify when we're writing it down, and we don't have to get lost in the weeds too much. So one main category was contact forces, and the other one, you might guess, does not involve contact. And these are what are known as field forces. And these do not require physical contact between the objects. It can exist, but it's not necessary. And so what causes these, or what are these? There's really four main ones. Sometimes people break them up into five. Depends on how exactly you look at it. So first one is the one we're going to be using the most, and one you're probably very familiar with, which is the gravitational force, which we're always going to abbreviate FG. Now, your textbook, and I've seen other sources occasionally abbreviate this as little w. I don't like to do that, but you'll see it happen. And the reason why is because gravitational force is literally the weight of something. So if I say that I weigh so many kilograms, or really, keeping it out of the metric system, let's go and say I weigh so many pounds, I'm really saying, what is the force of gravity being pulled down on me from the Earth's gravitational mass? So, everything on Earth has a weight, every object, so every object has a gravitational force, particularly if you're on any sort of planetary surface, the Earth, the Moon, anything like that. Now, so it's always present on Earth, and it's always directed downward toward the center of the gravitational mass that's causing it. So the Earth's gravitational mass, so the center of the Earth, that is where it's always directed. So that's why it always goes downward no matter what side of the Earth you're on. All right, the next one we talked about briefly with electric charge, we have electric forces. This is the forces due to positive and negative charges. We abbreviate FE. We will talk about this one this year as well. Now the next few, first you have the magnetic force. Now that is just the force caused by magnets. Once again, this is an AP Physics 2 topic. We're not going to talk about it too much this year, but feel free to ask questions about it. A lot of times electric and magnetic will be combined together into the electromagnetic force, but that's a bit of a point of contention. And the last one are what are known as the nuclear forces, which again come up more in AP Physics 2. Now those include what is known as the nuclear strong force and what is known as the nuclear weak force. Now the nuclear strong force has a lot to do with quarks, and specifically, why do nuclei stay in one piece? That is due to the nuclear strong force. The weak force has much more to do with radioactive decay. So when you talk about something being radioactive, you're really beginning to involve yourself with what is known as the weak force. So what are the main takeaways from this lesson on an introduction to forces? Now remember, this is just a brief overview of some basic stuff, so that from this point forward we can really start getting into more detail. So first off, can we classify matter in terms of being viewed as either an object or a system? So if I have a certain problem and I think about it as an object or a system, that matters. Can I identify key properties of matter, including its gravitational and inertial mass and its electric charge? Can I define what a force is? Go back and look if you're not 100% sure. And additionally, can we classify types of forces, not only into contact and field forces, but into subcategories below those? And can we identify which are present in a given situation? So you're going to see that in next class, that we will bring up some examples of some situations. I want us to start thinking about, okay, this force is present, this force is present, this force is present, and make sure we catch all the ones that are at least primarily going to be affecting the motion of objects.